Picture this. You're sitting at your computer,
Right.
and you've just spent, I don't know, 20 solid minutes carefully explaining a complex task to your favorite AI assistant.
Oh, yeah. We've all been there.
Right. You've given it all your specific preferences, the exact format you want, the specific tone to use, and it nails it. You're thrilled.
It feels like magic in that moment.
Exactly. Then 2 days later, you log back in, you ask it to do a nearly identical task, and, well, nothing. It completely forgets the strategy. You are right back to square one, feeding it the exact same instructions, watching it make the exact same beginner mistakes all over again. Have you ever been there? Because I definitely have, and honestly, it is incredibly frustrating.
It is a universally frustrating experience for anyone using these tools today. And, what you are describing isn't just a minor bug. It really highlights a massive fundamental blind spot in current artificial intelligence. We interact with these systems expecting them to learn from us over time, like a human coworker would. But in reality, they are just resetting. They are trapped in a perpetual present, essentially.
Which perfectly sets up our mission for today's deep dive. We are unpacking a brand new state-of-the-art paper from researchers at Google DeepMind and the University of Illinois Urbana-Champaign.
Yeah, UIUC.
Right. And the title is Evo-Memory, Benchmarking LLM Agent Test Time Learning with Self-Evolving Memory. It's a mouthful, but what they are tackling is this exact issue, something computer scientists call statefulness in AI.
Yeah, statefulness is essentially the ability of a system to maintain context and, remember conditions across multiple interactions over time. To be fair to current large language models, they do possess a very rudimentary type of memory.
Like keeping the chat history open.
Exactly. They can usually remember the literal words said earlier in a specific chat window. Like, if you tell an AI your dog's name is Buster, it will retrieve Buster's name an hour later as long as that specific window is open.
But remembering a static fact isn't the same thing as learning a skill.
Not at all.
And that seems to be the core tension the researchers are pointing out here. The AI remembers the chat log, but it doesn't remember the lesson it was supposed to extract from that interaction.
Right, and the researchers draw a very sharp line between two distinct concepts here. They call them conversational recall and experience reuse.
Okay, so conversational recall is...
Conversational recall is simply retrieving past facts, fetching Buster's name.
Got it.
Experience reuse, however, is the ability to abstract an underlying reasoning strategy from a past task, and then apply that strategy to a future novel task. Current systems are exceptional at conversational recall, but they fail fundamentally at experience reuse.
Okay, let's unpack this. Because understanding this mechanical difference between fetching facts and actually learning strategies is crucial to understanding why our AI assistants keep feeling like they're stuck in a Groundhog Day time loop.
It really is.
The researchers use a fantastic mathematical analogy in their paper, specifically in figures 1 and 2, to demonstrate this.
Yeah, they outline a scenario where you give an AI a standard single-turn task. For example, you ask it to solve a basic quadratic equation, something like 2x squared plus 3x minus 1 equals 0.
And the AI crunches the numbers and easily solves it. It tells you x equals -2 and 0.5. And it shows its work, proving it used the standard quadratic formula to get that answer.
Right. And because of that conversational recall we mentioned, if you ask it 5 minutes later, hey, what was the solution to that equation? It will perfectly recite -2 and 0.5.
Because it just looks at the log and reads the answer back to you.
Exactly. But the real test comes if you give it a brand new equation. Say 5x squared minus 1x plus 7 equals 0.
It essentially starts completely from scratch.
Completely from scratch.
It doesn't look at this new problem and say, oh, I see the pattern. This is structurally identical to the problem I just solved 3 minutes ago.
Yeah.
I should immediately jump to applying the quadratic formula again.
No, it doesn't do that at all.
It doesn't reuse the experience of solving the first problem to make solving the second problem faster or more efficient.
And that phenomenon right there is the illusion of memory. The system retains the raw data, but it throws away the workflow.
It reminds me of a student cramming for a history test.
Mm-hmm.
You know, the kid who memorizes exactly what year the Magna Carta was signed or the exact date of the Battle of Waterloo.
They have incredible conversational recall.
Right. But if you give them a new essay prompt, asking them to analyze the broader historical trends of why empires fall, they completely freeze up. because they didn't learn the underlying strategy of historical analysis. They just memorize isolated data points.
Yeah, whereas a truly great student understands the trends and can apply that analytical framework to any new historical event you throw at them.
Exactly.
That is a highly accurate way to conceptualize the gap. And, this limitation goes far beyond single-turn tasks like answering a math question. It severely handicaps AI in multi-turn tasks.
Multi-turn tasks being...
Scenarios where the AI has to take a long sequence of actions to achieve a goal. Imagine an embodied AI agent operating in a complex virtual environment, like a simulated household. Let's say its goal is to put a cooled tomato into a microwave in a virtual kitchen.
I mean, that sounds simple enough for a human. We walk in, spot the fridge, grab the tomato, walk to the microwave. Done.
Right, but for an AI, it requires extensive long-term planning and spatial reasoning. It has to explore the kitchen room by room. It has to locate the fridge, open it, find the tomato, verify that the tomato is actually cooled down, navigate across the room to locate the microwave, open the microwave door, place the item inside, and close the door.
That's a lot of steps.
It's a massive sequence of interactive steps filled with trial and error. What's fascinating here is that without experience reuse, if you ask that same agent to put a green cup in that same microwave the very next day, it wanders around the virtual kitchen, bumping into walls as if it's never been there before.
Oh, wow. So it has to re-explore the entire kitchen to find the microwave all over again.
It is doomed to repeatedly solve similar environmental problems from ground zero every single time it boots up. It never abstracted the broader spatial strategy of how to navigate this specific kitchen layout.
So we have this glaring fundamental blind spot. The AI is essentially a genius with amnesia. How are the researchers at DeepMind and UIUC actually proposing to fix this?
Well, they are attacking the problem by introducing a new benchmark and an entirely new framework called Evo-Memory. And the overarching goal is to force the AI to evolve during test time.
Let's clarify that term real quick. Test time meaning when the model is actually deployed, running in the real world and interacting with you and me, as opposed to its initial training phase in a massive corporate server farm.
Exactly. Test time learning is sort of the holy grail of continuous self-improvement during deployment. To test whether an AI can actually do this, the Evo-Memory Benchmark does something very clever.
Okay.
It takes standard static testing datasets and restructures them into sequential evolving task streams.
Meaning, instead of just giving the AI 100 random disconnected questions at once, it feeds them to the AI, one by one, in a highly specific chronological sequence.
Right, and this forces the model to constantly search its own recent history, adapt to the current problem based on what just happened, and evolve its memory bank after every single interaction.
Brilliant.
The researchers wanted to see if they could engineer an architecture that actually accumulates knowledge rather than just a chat history. So to do this, they proposed and tested two specific methods against these sequences.
Let's break those two methods down, because this is where the engineering gets really cool. The first method they propose is called XPRAG, which stands for Experience Retrieval and Aggregation.
Yeah, XPRAG is designed as a simple, bare-bones baseline. Essentially, when the AI faces a new task, it searches its memory for past experiences that seem semantically similar. It grabs those raw logs, dumps them into its current context window, and uses that text to try and generate an answer.
Okay.
And then after it finishes the task, it just appends that new raw log directly into its memory bank.
Wait, if the AI is just retrieving its past raw logs and dumping them into its context window, isn't it just copying itself?
Pretty much, yeah.
If it's merely adding to a giant, never-ending list of everything it's ever done, how does it actually improve? Doesn't a system like that just eventually overwhelm itself with its own data?
You've identified the exact bottleneck of the XPRAG method. It performs what researchers call one-shot experience reuse. It's marginally better than having zero memory, sure, but it lacks iterative reasoning.
It's just hoarding.
Right. It doesn't actively adapt, summarize, or refine what it knows. It just hoards data. That hoarding is exactly why the researchers introduced their second, vastly more advanced pipeline, which they call REMEM.
REMEM.
Yeah.
Which is short for, I assume, refining memory?
Yes, it's a continuous action-think memory refine pipeline. It synergizes reasoning, acting, and memory refinement into a single decision loop. This is where we completely depart from the data hoarding of XPRAG. REMEM introduces an active third dimension of memory reasoning.
Okay, so how does that actually work mechanically? I think this is where a lot of people get lost. How does a frozen language model actively refine its own memory? I mean, is it rewriting its own code?
No, it's not rewriting its core code, but is rewriting its own internal reference materials. The researchers structured this as a decision-making flowchart with 3 specific selectable operations.
Okay.
When faced with a task, the agent can actively choose to do one of 3 things. It can think, act, or refine.
Okay, so think is the internal reasoning, like the AI talking to itself in a hidden scratch pad, decomposing a complex task into smaller, manageable steps before it takes any real action.
Exactly. Then there is act, which is executing a tangible operation in the environment like opening that virtual microwave door or producing the final text response to the user.
Right.
But the true mechanical breakthrough is the third operation, refine memory.
The meta-reasoning step. Walk me through exactly what happens when the AI chooses refine.
So when the AI triggers the refine operation, usually after finishing a task, it pauses and actively evaluates its own recent performance. It looks at the log of what it just did and retrieves relevant past experiences.
Like XPreg does.
Like XPRAC, yes. But instead of just dumping them together, the model is prompted to synthesize a generalized rule. It acts like an editor.
Oh, I like that.
It preens the noise, extracts a successful strategy, and writes a concise summary of how to solve that specific type of problem. It then saves that synthesized rule into a dedicated memory pool.
It turns memory from a passive read-only text file into an adaptive living database that interacts with the AI's reasoning in real time.
Exactly. And it actively discards the dead ends it took to get there. It only saves the lesson.
Here's where it gets really interesting for me, visually. If we think about the baseline memory, like XPreg, it's basically a messy junk drawer in your kitchen.
Oh, absolutely.
Every time you complete a task, you just toss the raw receipt, the 50-page instruction manual, and the spare screw into the drawer. After a few weeks, you can't find anything because you have to dig through mountains of useless context just to find the one screwdriver you need.
The retrieval process becomes computationally heavy and incredibly inaccurate.
But ReMem is entirely different. ReMem is like having a self-organizing filing cabinet. Every time you finish a project, ReMem actively looks at the paperwork, throws away the junk drafts and the spare screws you don't need, writes a one-page summary of the key takeaways, and files it in a perfectly labeled folder.
That's a great way to put it.
So the next time you face a similar project, you pull out exactly the right strategy immediately without the clutter.
That filing cabinet analogy perfectly illustrates the refined operation. But of course, the big question in any academic paper is, does this beautiful theoretical framework actually translate into hard, empirical data? Does ReMem actually make the AI smarter, or does it just add unnecessary processing time?
Let's look at the numbers, because they tested this framework across multiple cutting-edge models, specifically running it on Gemini 2.5 Flash and Claude 3.7 Sonnet. And the leaps in performance are substantial.
Huge. Let's return to the baby AI environment, which is that multi-turn, embodied, virtual kitchen navigation task we discussed earlier. Using the ReMem pipeline, the AI agent achieved a massive 0.92 success rate and a 0.96 progress rate.
Translating that, it means the agent is succeeding almost 100% of the time in complex spatial environments where the baseline models were just wandering aimlessly in corners.
Yeah, the data also revealed a fascinating detail regarding task similarity. On the Gemini 2.5 Flash model, they found a Pearson correlation of R equals 0.717.
Okay, for those of us who haven't taken statistics in a while, a Pearson correlation measures how closely two things are related. A score of 1.0 means they move in perfect lockstep, so 0.717 is a very strong positive link. But what exactly is linking up here?
Good question. The researchers were correlating the structural similarity of the tasks with the performance boost provided by ReMem. To put it simply, datasets that involve highly repetitive, recurring structures like complex spatial planning tasks or navigating a household environment saw massive performance gains.
Because the AI could easily extract a rule about the environment and reuse it constantly.
Exactly. Conversely, when they tested datasets that are highly diverse, where every question is wildly different.
Like the GPQA dataset, which is a mix of graduate-level biology, physics, and chemistry questions.
Yeah.
Or the AIM-25 dataset, which is elite, varied math Olympiad problems.
Right. In those highly diverse datasets, ReMem still helped, but the gains were much smaller. There were fewer transferable experiences to extract. I mean, a rule about physics doesn't help you solve an elite geometry puzzle.
Right. If every problem is completely alien in the last one, having a beautifully organized filing cabinet doesn't help you much because every folder is empty. But if you are doing household tasks every day, knowing the layout of the kitchen is an absolute game changer. Which brings us to the efficiency metrics. This is where the paper really shines for me.
The steps to complete tasks data is perhaps the most practical takeaway for everyday users.
Because it's not just about getting the right answer eventually. It's about how much computing power and time the AI expends to get there.
Yes. On a household navigation benchmark called AlfWorld, the baseline AI models took an average of 22.6 steps to complete a given task.
22.6 steps of just wandering around, trying things, failing, backtracking, trying again.
Right. But when they applied the REMEM framework, that number plummeted to just 11.5 steps.
That is wild. It literally slashed the required reasoning and action steps in half.
It did. REMEM doesn't just make the agent more accurate, it makes the agent's internal reasoning significantly more concise and focused.
Because it already has the summarized strategy. It doesn't have to bump into the virtual walls to figure out where the microwave is. It pulls the folder from the filing cabinet, reads the summarized map, and walks straight to the appliance.
And this specific efficiency leads us into a crucial experiment the researchers ran regarding feedback and failure.
Oh, this part is fascinating.
They wanted to know what happens when an AI's memory bank is filled not just with its successful tasks, but with its complete failures as well.
Which makes sense, because in the real world, you try things and they don't work. Your memory isn't just a polished highlight reel of your best moments. You remember the times you messed up.
Exactly. So the researchers fed the baseline AI models a raw mix of successful task logs and failed task logs. And the baseline models effectively crashed. Their performance just plummeted.
Why? I mean, if they have more data, shouldn't they make better choices?
You would think so, but the baseline models got entirely confused by the noise of their own failures. When they searched their naive, hoarding memory, they pulled up the failed strategies right alongside the successful ones, and the model couldn't reliably distinguish which workflow actually led to the goal. The presence of failure introduced too much noise, disrupting their subsequent reasoning.
So going back to our filing cabinet analogy, the baseline model just stuffs the cabinet with every draft of a document. When it needs an answer, it pulls out a draft filled with errors, assumes it's correct because it's in the cabinet, and executes the wrong strategy.
That's exactly what happens. REMEM, however, stayed incredibly robust under these exact same conditions. It didn't degrade at all.
Because of that refined step.
Yes, REMEM actively prunes the noise. When REMEM is forced to look back at a failure, its meta-reasoning process analyzes why the failure occurred. It extracts the negative lesson. For instance, I learned that trying to put a metal bowl in the microwave causes a failure state.
Right.
It writes that specific rule down and discards the useless mechanical log of the failure itself. It learns from the failures without repeating the mechanical errors.
That is such a uniquely human way to process information. We don't just remember the raw data that we touched a hot stove. We extract the abstract rule, stoves are hot, and file that away so we don't have to touch every single stove we ever encounter just to verify it.
Yeah, and this transition from processing failure to processing difficulty brings us to another fascinating aspect of their research, which is the easy versus hard task sequence.
Right. The researchers wanted to see how these memory models handled sudden spikes or drops in task difficulty, which they outline in their third research question.
They took the sequential task streams and organized them in two distinct directions, presenting a long sequence of easy tasks followed immediately by hard tasks, and vice versa, hard tasks followed by easy tasks.
And the results were drastically different depending on the system. When the baseline methods, the ones without the self-evolving filing cabinet, moved from easy tasks to hard tasks, they suffered massive performance degradation.
The technical term is that they broke under the distribution shift. A distribution shift happens when the underlying rules or complexity of an environment change unexpectedly.
Okay.
The baselines had essentially overfit their retrieved memories to the easy problems. So when the complexity suddenly spiked, their rigid, hoarded data was entirely inadequate to solve the new challenges, and they couldn't adapt.
But REMEM maintained its performance. It didn't break under the shift. And even more impressively, in the hard-to-easy sequence, REMEM hit an incredible 0.94 success rate and a 0.97 progress rate. It proved it successfully retained the advanced transferable knowledge from the difficult tasks and applied it flawlessly to the easier ones.
It did.
So what does this all mean? Because I actually have to push back a little bit on the premise of this specific test.
Okay, go for it.
The researchers point out that the baselines fail when jumping from easy to hard. But human learners suffer if you jump from an easy middle school math worksheet straight into advanced college calculus. If you jump from easy to hard too fast, human brains break down too. Isn't it a bit unfair to expect a machine learning system not to stumble when the difficulty suddenly spikes like that?
It is a demanding test, absolutely, but it's necessary to prove whether true abstraction is happening. If we connect this to the bigger picture, the researchers use this to stress the importance of structured task progressions.
Okay.
It's not about expecting the AI to magically bridge an impossible gap and invent calculus on its own. It's about recognizing that, just like humans, AI requires a well-structured curriculum to maximize its learning.
But if humans crash when the curriculum skips steps, why penalize the baseline AI for crashing?
Because of how it crashes. When a human struggles with calculus after only learning basic addition, they don't suddenly forget how to add.
Huh.
The baseline AI models, when faced with the massive complexity spike, often became so overwhelmed by retrieving useless, easy strategies that their overall reasoning degraded entirely. They forgot how to add, so to speak.
That makes sense.
ReMem, on the other hand, stays stable under these shifts. It doesn't mean it instantly solves every hard problem. It means the architecture successfully abstracted the underlying concept of the early tasks.
You built the foundation.
Exactly. It is building a foundational understanding that can scale up or scale down. The baselines failed because they simply memorized the specific sequence of buttons they pressed to get the easy answer. ReMem succeeded because it actually learned the subject matter.
That is a phenomenal distinction, and it completely shifts how we should view these tools. We are looking at the critical leap from treating AI as a static, passive search engine to treating it as a lifelong, self-evolving agent, an agent that gets sharper, more focused, and more efficient with every single interaction. We saw it literally slash its effort in half in the AlphaWorld test from over 22 steps down to 11. It is genuinely learning how to operate in its environment.
It represents a fundamental paradigm shift in how we engineer long-term AI capabilities. It's no longer just about expanding the context window to hold massive, ungodly amounts of raw data. It's about engineering the architecture to actively reason about what that data means, summarize it, and curate it for the future.
So to you, the listener, the next time you get frustrated at your AI assistant for forgetting your preferred workflow or, for making you explain your coding style for the 50th time, take a breath. Know that the exact limitation you're experiencing is actively being solved in the lab. Self-evolving memory architectures like ReMem are being built right now to fix exactly that, turning these models from forgetful, isolated assistants into lifelong, compounding collaborators.
It is an incredibly exciting frontier, but it also raises an important question, and it's a thought I want to leave our listeners to mull over today.
Ooh, lay it on us.
We've seen today that the researchers proved ReMem succeeds largely because it perfectly curates its own memory. It actively prunes out the noise of its past failed experiences to hyper-optimize its future actions.
The perfectly organized filing cabinet with all the rough drafts thrown in the trash.
Exactly, but if we examine human learning, our messy, noisy mistakes, the things we did entirely wrong, the bizarre tangents we went down that failed completely, those are often the very things that lead to unexpected creative breakthroughs or happy accidents months or years down the road.
That's so true.
True innovation rarely comes from perfectly pruned, highly optimized efficiency. It often comes from the friction of the noise.
Wow. If you throw away the rough drafts, you might throw away the one weird idea that could have been a masterpiece.
Exactly. So the question is, if we engineer artificial intelligence to ruthlessly prune away its failures for the sake of task efficiency, might we be accidentally deleting the very noise required for true, unexpected innovation?
That is an incredible point. Are we optimizing away the messy magic of learning? A huge thank you to the researchers at DeepMind and UIUC for a truly perspective-shifting paper. And thank you all for joining us on this deep dive. Keep questioning the noise.